It is physical science time, you're exactly right. It is physical science time. Let's talk about electric current. Oops. So I wish I had phrased this differently because I told you the last lesson we talked about was static electricity. So this one could be called current electricity, which I wrote electric current, but whatever. So electric current, and just write this down real fast. We talked about this a little bit in the last one, but how can we define current? Current is
like
the movement of, I like that start, of what?
Well, it could be anything.
Electrons. Current is the flow of electrons from... We're going to finish this, but how did heat flow, generally?
Down from the below to higher.
Not always. I'm looking for something slightly different from that. Heat always flowed from warmer to cooler. Yeah, thank you, Jacob. From warmer to cooler. So current is the flow of electrons from, can you guess? It won't be from warmer to cooler.
From negative to positive.
Yeah, from places of high negative electric charge to places of low negative electric charge. From places of large negative charge to small. Or from negative to positive. We can also think of it. Negative to positive. This analogy is used a lot when we're talking about like the theory of electricity or electrical circuits even. We a lot of times think of electric current kind of like the flow of water. So in the case of what we call voltage, it's the difference between where the electrons are flowing from and where they're flowing to. And the analogy that's often used for that is like a water tank or a water tower or a water bottle, right? Something that's storing water. You can think of like your water bottle, when you're squirting into your mouth, you're squirting it from a place of a lot of water to a place of little water, right? What we call in water terms, when we talk about rheology, which is the study of how water flows, it's from high head pressure to low head pressure. When the way a water tower works is that when you flush a toilet or turn on a sink or something, the water flows from up high to down low, right? In fact, we usually say water flows how? Water flows downhill, right? Water flows downhill. But what it's really doing is flowing from high head pressure to low head pressure. In the same way, current is the flow of electrons from high voltage to low voltage. So let's talk about that. Voltage equals we can kind of think of it almost as, it's not, but let's put approximately to, the storage of electric charge. So in the same way that a water tank is the storage of water, what would be the storage of electric charge? What would store electric charge?
The water?
No. That was an analogy.
Oh.
What stores electric charge? You know what it does.
A what?
No? What stores it? What holds the electrical charge so you can use it later?
Metal.
The battery.
A battery. Hey, I got one. Boom. And how do you know this about batteries? What would you call this?
A battery.
What kind of battery? A 9 volt battery. We measure the quality of a battery, this kind of battery, as in volts, in its voltage, right?
So
a lot of times you'll hear an old timer, my grandpa, my dad, would say something like, regarding an electric fence or a car battery or the outlet on the wall, they'd say, it ain't, they would say, it ain't the voltage that kills you, it's what they would call, an old person will call it as amperage. And we'll get to amperage in a second. But effectively, like that, when we did the Van de Graaff generator and we all held hands and got shocked, there was probably something like 50,000 to 100,000 volts of electricity, which is a lot compared to like the 110 volt electrical outlet. There's a lot of charge, right? But what's affecting you, what can possibly kill you, is not the amount of charge that there is, in the same way that we could have a whole lake of water stored behind a dam, but that's not going to affect anyone. What is actually going to be damaging about that dam is how it flows.
How strong?
how strong or how quickly or how fast it flows. And in the same way, the amount of charge is not what can possibly damage a person, but it's how quickly it's moving through that person, right? How much it's moving through that person, which can stop your heart. So people do get electrocuted, right? Electrocuted is no, you haven't, because I was going to say this. Electrocute, that word, is what we call in English a portmanteau, which is a combination of two words of electricity and execution. So when you get electrocuted, that only happens to you once, because what has necessarily happened?
You die.
You've died. Yes, you've been killed. Electrocute, that word electrocute means that it killed you. So you have not been electrocuted. You may have been electrified, but you have not been electrocuted. Although, probably I'm certain there is someone out there who's been electrocuted and is now still alive, because they do the exact same thing to bring you back to life. They defibrillate your heart. But anyway, so back to this. We can think of voltage as how much electrical, sometimes we call it this, electrical, write this down please, electrical potential. That's another word for the voltage. Electrical potential, which is the difference in charge. In fact, it's reflected in our symbol for a battery, which is, this is the symbol we use in circuits for a battery. It has a small electrical charge and should be the other way around, sorry. A small electrical charge, or a small amount of electrons, and a large amount. The plus and the minus are not usually indicated, but when you do a battery on a circuit diagram, it's shown in this way: one short line and one long line. Speaking of battery, in our laboratory, we use batteries to make a what?
Circuit?
Yeah, circuit. An electrical circuit. Can you think of what other word is circuit probably related to?
A circle.
A circle, right? It has to form a loop, what we call a closed circuit. So if we have the battery, the electrons will flow how? From what to what? From negative to positive. So the electrons are going to flow out this wire through I'm going to draw a little light bulb here. Oh, no, it's good.
Scoffed.
There we go. And then back into the battery in the positive, right? The electrons are going to want to flow from negative to positive. So they're flowing, and this gets, I should note right this second, this gets confusing pretty quickly, because if I remember correctly, obviously in science what's actually flowing are the electrons, so it is flowing from negative to positive, but for some reason, I'm not even sure if this is 100% true, but I remember that like in electrician school or something like that, the custom is that charge flows from positive to negative. Like they actually call the larger amount of electrons positive. Don't worry about that right this second. You should know that electrons flow from a place where there's a lot of electrons to a place where there are few electrons. That's how it moves, right? So the electrons are moving along here, and what happens is as they get to this little light bulb, which we call a load, anything that's being powered by the electricity we call a load. Battery. But what's this line I've drawn? What do we call that?
A wire.
I'd call it wire. You might call it conduit, but so once the electrons get to this load, what happens here? They don't just keep traveling smoothly. Do you know what's happening inside of here?
It goes up in the little coil, then heats up, then goes
Exactly.
down, then goes
So yeah, so this serves the purpose of what we call this specific load. Not all loads are this, but this light bulb has a special kind of metal in it, tungsten, that acts as a resistor. And what happens is the electrons no longer can flow smoothly through this nice copper wire. They meet resistance, right? So they have to bump into stuff, and as they bump into stuff, it heats up. In the case of our light bulb, it heats up real hot, and it heats so hot in a normal light bulb that it glows bright, right? That's what. No, these are LED lights, which work on a different principle. There's something called a light-emitting diode, which uses different substances that, as the electrons flow through that substance, they emit light in a different way. This is what's called an incandescent light. You might as well write that down. Whereas an LED stands for light emitting diode. A diode is a different thing in circuits, but basically it's a piece of some kind of metal that when the electrons flow through it, it emits light, usually much, much cooler than an incandescent light does. Anyway, so it flows through the load, and then it flows up to the positive end of the battery. If we have here somewhere, I'm going to show you this in a second, but we use this symbol to mean a resistor. This is just a normal resistor.
It's your heartbeat.
And what a resistor does, first of all, the concept of resistance you know what resistance is, right? Like if you meet resistance in your daily life, that means that someone has opposed you in some way, right? Like
It makes it harder.
yeah, it makes it harder. It makes it harder for the electrons to flow through. So what would that do if we put this resistor here? What would it do to this light bulb?
Make it dimmer.
Yeah, exactly. We're going to show that in a second. And these things, voltage, current, and resistance are related in this way. V equals IR, where, and we love equations. We all love and memorize equations. V is, what can you guess?
Voltage.
Voltage. Measured in, I'm going to have to check, I'm sorry. Volts. Well, I didn't really have to check. I is current, measured in, can you guess?
Current.
No. I gave you a hint earlier. I said this is what old people. What do you remember? What? Yeah, amps. Amps, which is short for amperes. Amperes, which is. I wonder if your book even says this. No. An ampere is the SI unit for a current. It's a base unit. And then R is resistance measured in ohms. This is a Greek letter, capital Omega.
That looks like Squidward.
Sure. And this word is ohms. It's named after a guy.
Wait, what's that symbol?
So make it like this. It's the capital Greek letter
It
Omega.
looks like Squidward.
You can make it, if you want, you can just do a simple one like that. I always do the little serifs on the end because I think it makes it look nicer. It almost looks a little bit like our...
Squidward.
No, not our Squidward. It almost looks a little bit like our...
Light bulb.
Well, okay, but also like our other cooler thing.
Oh, the little thingy that you stuck your hand on.
Does anyone remember what I just told you it's called?
Someday.
Something Day. No, come on. Van de Graaff. It looks a little bit like the Van de Graaff generator. Anyway, so the nice thing about this is just like our equation for Q equals MC delta T, right? Remember that one? This is really easy to manipulate. If I wanted to find current instead, what would I have to do?
Just divide.
Yeah, V over R equals I. If I wanted to find R instead, V over I equals R. Just make sure your units always match up. So I want to show you something. Pull those blinds all the way down, please.
Because then the penny is the graphite is going to have a resistance.
Well, while they're pulling those blinds down, please do it quietly so I can keep talking in the video. Your book differentiates, and you should probably be aware of the difference between what are called dry cell and wet cell batteries, but I'm going to trust you to read about that. So listen, please. Show me that you're listening. In your book, read about dry cell and wet cell batteries, or you can look them up online if you're watching the video and you don't have access to the book. And then another thing, yeah, just grab it real quick.
Jump.
You're almost there.
Hey, I got it.
You can stand on the little, that thing. Yeah, stand on that little thing.
You
Yeah,
see,
there
I'm
you
so
go.
tall.
There you go. Good girl. Okay, Tammy, hit the lights. Oh, not yet.
Oh, here.
Thank you for not hitting the lights yet, Tammy.
What?
I have some stuff here.
Are you being
Shh. Okay, please. Okay, so I have here battery, right? We're going to basically make this thing I drew on the board. Battery, I'm going to start with, the negative end is this large terminal of the 9-volt battery. And what color should I attach, which color wire should I attach to the negative end of the terminal?
Doesn't matter.
It doesn't really matter, but customarily
Black.
we attach black to the negative end. So I'm going to attach my black wire there. I want this to be able to be seen. Shh. I don't really want to, I know what I'll do.
Raise your music stand.
I could, but it doesn't stay up very well, so I'm just going to switch back to this so now you can see a little better. Okay, I'm going to touch my positive wire to this one. Whoop. And then we're going to do it without, there will still be some resistance. All wires have some resistance, but for now we're going to do it without a special resistor. And I'm going to attach the negative to that, and the positive, and I want you to hit the lights now, Kami.
I was got it actually.
Aww! Look at that!
That's a very bright little light.
Yeah, so look, check it out. That really is a bright little light. I got my battery.
Christmas tree.
Battery, right? The electrons are flowing from the negative end of this battery. Once again, I think it's actually positive. You look it up sometime, but I don't know how it got switched around in the of electricians, but so basically the electrons are flowing from the negative terminal of this battery through the wire, through the little light bulb, which is going to blind me, making the light bulb filament, what we call the filament, really, really hot because it has a higher resistance, and then that's glowing because it's so hot, and the electrons continue to flow out and through this. Now what I'm going to do, oh dang it, I need another, Carter, run and go
Not
get
really.
the very back in that cupboard,
Just touch it.
wooden cover on the bottom. I need another red wire, please. Do you know what I'm talking about?
Can we
The
leave the
Yeah,
lights
the one
off?
from.
yeah, there's 4 wooden cupboards. Yeah, and the third one.
Can we leave the lights off
Well,
and use
well,
your
yeah, look.
Christmas tree as a light?
Is this my Christmas tree?
Yes.
Look how bright it is. It really is hurting my eyeballs to look at it in the dark like this. This is a nice little light bulb. And also 9 volt is really quite a lot for a battery. You know how much what the voltage of like a AA battery is about 1.5. So it'd take 6 of those to make the voltage. Thank you of this. And then so what I'm going to do now is attach in between. That was bright. In between, I'm going to separate the current on the positive side. No, that's... Well, actually, this might serve our purpose, because we might be able to tell which way the electrons are actually flowing. Where'd my little lead go? Light, please. Oh, I found
You
it.
have
I
a
found
light
it.
right there.
No, I don't. Ew, that's disgusting.
Turn it off, please.
You literally have a light right beside you.
Use your phone flash.
Okay, check it out. So now I have resistance in the form of, this is just pencil lead, right? It's not actually lead. What you know what it is?
Graphite.
Graphite. And the further, hopefully,
The dimmer it gets.
yeah, the further away I make it on here, the dimmer it gets. Oh. Because there's more what, basically?
Resistance.
Yeah, right. The graphite is a resistor, and the further apart I make these wires,
Let's
the
see
dimmer
the
there.
comparison.
Yeah, hold on a second. Let me try it the other way to see if it works better. I think for one thing, the voltage on this might be just a little bit too high for this to make to do it exactly how I want to do it. But now it ain't working at all. Anyway, circuits. Circuits, what a treasure. Turn that light on so I can say bye.
What about the penny?
Oh, the penny was just
Oh,
the penny
well,
came with
that's
one of the wires. Okay, bye.